Have you ever looked at some huge, complex electrical system and just wondered, how does all that work without, just blowing up? Well, it turns out one of the biggest secrets is this really simple but incredibly powerful rule. And today we're going to unravel a massive industrial mystery using a law that, believe it or not, you can totally understand just by thinking about a simple mountain hike. All right, so let's dive right into this high-stakes puzzle. We're heading into the world of some serious heavy industry. I'm talking places that use just mind-boggling amounts of electricity every single day. And this isn't some dry textbook problem. Oh no, this is where the theory gets real and really, really powerful. So here's the core question, the big mystery. How in the world can one single electrical circuit have both positive 500 volts and negative 500 volts at the exact same time? I mean, that just seems to break the rules of basic math, right? How can you have both on the same wire? It really feels like a paradox. Well, this puzzle comes from a very real place, an aluminum smelting plant. What you're seeing here is something they call a pot line, and really, it's just one gigantic circuit. Think of it like hundreds of individual smelting pots all connected end to end in a single massive line. In electrical terms, we'd call that a series circuit. And let me tell you, this circuit is an absolute beast. We're talking about it operating at over 1,000 volts. So how do they do that? Well, they link up 240 of these smelting pots, one after the other. Each pot kind of uses up, or as engineers say, it drops, about 4.2 volts of electrical pressure. So you just do the math. 240 pots times 4.2 volts each, and that gets you a grand total of 1,008 volts from one end to the other. And this is where it gets really, really weird. Because if you take a voltmeter and stick it right in the dead center of this massive line of pots, and then measure out to each end, you get something strange. On one side, you read positive 504 volts, and on the other side, negative 504 volts. It's positive and negative at the same time. To figure out how that's even possible, we actually need to leave the factory for a bit. Okay, to solve this industrial puzzle, we're going to do something that might seem a little weird. We're going to completely forget about electricity for a minute. Instead, we're going on a hike. Stick with me here. I promise this simple analogy holds the key to everything. So I want you to imagine a hiker on, say, a 4-day truck. They start out at their base camp, let's call it point A. They go on this big hike, and at the end of the 4th day, they complete a full loop, ending up at the exact same spot they started from, back at point A. Okay, let's look at their journey day by day. On day 1, they climb up 1,000 meters. Nice. Day 2, they go up another 400. Then they start heading down, losing 1,100 meters on day 3, and then another 300 on the last day. So here's the question. When you add up all those ups and downs, all the gains and all the losses, what is the total change in altitude for the whole trip? Well, it's 0. Of course it is. They ended up right back where they started. This is one of those things that's just fundamentally true. It's intuitive. If you walk in a complete circle and end up right back at your starting point, your net change in elevation has to be 0. It doesn't matter how high you climbed or how low you dipped in the middle. The total change is 0. Remember this rule. It's the key. Okay, so a mountain hike. What does this have to do with our electrical puzzle? Well, let's connect the dots because we're about to apply this exact same logic to how electricity flows. And you know what? The connection is shockingly direct. Think of it like this. The altitude in our hike, that's just like voltage, the electrical potential in a circuit. The hiker's path, that loop they walked, that's the electrical loop, the path the current takes. And that reference point we use for height, sea level, in electronics, we just call that ground. And this brings us to the official fancy name for our mountain rule when we talk about electronics. It's called Kirchhoff's voltage law, or KVL for short. And all it really says is that in any complete circuit loop, the voltage you gain from your power source, like a battery, has to be perfectly balanced out by the voltage you lose or drop across all the things in the circuit, like light bulbs or motors. The grand total always, always adds up to 0. It's really just a statement about the conservation of energy. All right, now we're armed with our mountain rule for electricity, Kirchhoff's voltage law. Let's head back to that smelting plant and finally crack this 1,000-volt puzzle. So the whole secret to this mystery, the whole positive and negative 500 volts thing, it has absolutely nothing to do with the circuit breaking the laws of physics. Not at all. It's all about your reference point. It's about where you decide to start measuring from. It's all about where you define your sea level. And that is precisely what the engineers did. They took that long line of 240 pots, and they very cleverly established their 0-volt reference point, their ground, right smack in the middle of the line, right after the 120th pot. So if you stand at that center ground point, the voltage climbs up to positive 504 volts in one direction and drops down to negative 504 volts in the other. But here's the key. The total voltage difference all the way from end to end is still 1008 volts. And if you trace that entire loop, the full 1008 volts from the power source is perfectly used up by all the pots. Kirchhoff's voltage law is satisfied. And just like that, mystery solved. Now, this whole idea of a ground, a reference point, it is so much more than just a clever engineering trick for big factories. In fact, it's one of the single most important safety features you have in your home. It's the reason you can plug in your toaster or your TV without worrying about getting a massive, dangerous shock. Okay, let's imagine your toaster has a problem. A hot wire inside comes loose and it touches the metal case. Suddenly, the entire metal body of the toaster is live with electricity. If you then walk over and touch it, your body becomes the easiest path for that electricity to travel to the ground you're standing on. And that is an incredibly dangerous, potentially fatal situation. But this is where the ground wire comes in. It's that third prong on the plug. That wire connects the metal case of the appliance directly and safely back to the earth. So now, if that same hot wire comes loose and touches the case, the electricity doesn't need to go through you. It has a super easy, super low resistance path to follow right down that ground wire. This creates a massive surge of current that instantly blows a fuse or trips your circuit breaker, shutting off the power and keeping you completely safe. So really, that's what grounding is all about. It's providing a safe, alternative loop for dangerous electricity to go. It is a direct, life-saving application of the exact same principle we saw with our mountain hike and that industrial pot line. It's all about defining a safe zero point for energy to escape to, and in doing so, it protects all of us. Which brings us to one last big idea to chew on. Kirchhoff's law, at its heart, is really just a statement about the conservation of energy. It's saying that if you travel in a closed loop and end up where you started, you can't have magically created or destroyed energy along the way. That's a fundamental truth that goes way beyond just hikes and electrical circuits. So it makes you wonder, where else in the world around us, maybe in everything from the path of a roller coaster to the orbit of a planet, do we see this simple, powerful zero-sum rule at work?